Okay, so I've said everything technical I have time to say. So what I'm going to do is I'm going to give you kind of an overview of some of the other results that we don't have enough time to cover. And each of these are chapters that haven't been written yet. Yes?
About the last lecture, about
Mm-hmm.
renaming. What's the connection to order-preserving renaming?
So order-preserving renaming, I don't think. So if renaming is impossible, then order-preserving renaming is impossible. The algorithm that we looked at is not order-preserving.
There's
So.
a mobile for order-preserving renaming.
Mm-hmm.
It's exponential.
Yeah.
Number. So it's 2 to the n times n.
Yeah.
Maybe.
Yeah, in synchronous models, there's a logarithmic lower bound.
Yeah.
But that's in some sense, a pretty different problem.
Yeah.
So in other words,
It's a lot more structure.
yeah.
It's quite smaller. So actually, already the original paper, I think, gave a type 1 for asynchronous situation. And it's pretty simple, actually.
Yeah, and the synchronous is pretty easy too, because you can actually build a construction that runs for log n time. Basically, you fail enough processes and create enough uncertainty, so you never quite know what your position is until you've failed all the processes. Okay, so one issue that comes up is robustness. What does this mean? So I have imagine I have two black boxes, A and B. And let's say A solves consensus for 2 processes, but not 3. And let's say B also solves consensus for 2 processes and not 3. Can I combine them using some read-write memory, for example, and get something that is more powerful than either one by itself? And the answer is that yes, you can, but all the examples are really pathological. In the following sense, that imagine that A is something that will solve consensus, but only if you convince it that you can solve weak symmetry breaking. So it knows what the answer to consensus is, but it won't tell you unless you basically give it a certificate that says that I've solved a weak symmetry breaking. And imagine that B is something that solves a weak symmetry breaking, but not consensus. So by themselves, neither one of these will solve consensus, but if you put them together, then they'll solve consensus. But the reason this is pathological is because in some sense, this module already knows what the answer is, it just won't tell you. And so this isn't really, if you're interested in questions like what kind of machine architectures do you need to solve these problems, designing a chip that solves consensus but won't tell you is probably not something that Intel is very interested in. So there's a sense in which, yes, you can get these violations of robustness. That is, I can take 2 things that are individually, we can put them together, but there's something kind of weird and unsatisfying about it. So there was, in fact, a couple of papers that claim that if the sequential specs were deterministic, then this didn't happen. And I think the result is, there's another case where the result is true, but I don't think anybody believes the proofs in those papers. But there's another paper that basically gives a very simple topological condition that says that under these circumstances, you can't combine things and get more power than you can from the original things. And actually, the topological condition has to do with zero connectivity of complexes. And then proving that it's tight involves a lot of simulation arguments. So that's one thing that can be done. Another question is classification. So we did a little bit of classification at the beginning where we said that set agreement is harder than weak symmetry breaking. So in other words, if I can solve set agreement, I can solve weak symmetry breaking, but there's at least one model where it doesn't go the other way. And so we're interested in saying, well, is there some way of classifying how powerful particular tasks are. If I give you a black box that solves some task, under what other tasks can I implement with it? Can I come up with hierarchies of tasks where each one is more powerful than the other? So it turns out that so Sergio and I came up with something we call loop agreement, which I think we mentioned earlier on in different contexts, where what it is, in this case, G here is a finitely presented group, big G, and little g is an element of the group. Now, what we can do is we can turn this into a task that involves taking 3 processes and having them rendezvous along a particular path in a complex. So we can take this group and turn that into a complex. This is clearly not the kind of problem that comes up in everyday life. This is a contrived problem that is set up to answer a particular question. But what we can show is that a box that implements this, if I give you a black box that implements this and I want to implement that, then I can do that if and only if there's a group homomorphism carrying G to H that also carries little g to H. So what that says is that if you look at the hierarchy, you get a really rich structure, because I can build an infinite tower of these things by sort of appending more and more elements to the group. So that says that I can find basically an infinite hierarchy of tasks where each one is more powerful than the other, and there's no weakest task, because I can always go arbitrarily far in either direction. It also says I can find a countable number of tasks, all of which are incomparable in the sense that neither one implements the other one. And so it turns out that there are reasons that it's very hard to generalize beyond 3 processes, because this theorem here has a topological version which even the topologists haven't been able to extend beyond 2 dimensions. So there's some kind of hard problems here. But it does say that the classification, if you look at arbitrary tasks, is pretty wild. There are a lot of open questions about if you restrict tasks to be something a little bit more reasonable than what the classifications look like. So for example, suppose all your inputs and outputs are binary. What does it look like? And that's still kind of an open question.
And without topology, it's not known how to
Well, without what we do here is we just say here are tasks, that have this property that this implements that implements that, but not the other way around. And so the topology allows you to prove this sort of, this is the result that gives you all the structure. And you need a combination of algebraic topology and other things. I didn't do this here because this involves all kinds of group theoretic stuff that I wasn't ready to go over. There's the decidability. We mentioned this a little bit early on in the class. So here the idea is that if we had a Turing machine that could decide whether a task is has a protocol, then we could fire all our grad students and just have Turing machines write papers for us. And the answer is in some models, for certain kinds of problems, the answer is yes, it's decidable. And that's because the question of decidability reduces to 0 connectivity, that is, graph connectivity, which is decidable. And sometimes no, because it reduces to k connectivity, where k is greater than 1. Now, the interesting thing here is that k connectivity, determining whether a complex has no holes, is decidable below 2, and it's actually decidable above 2. But for 2, it's not decidable, which is an odd thing. The reason is that it boils down to something called the word problem for finitely presented groups. And in dimension 2, the particular groups you're looking at can be any group, which is known to be undecidable. If you go above dimension 2, then the groups are all abelian. And a word problem is decidable for abelian groups. I don't know any way to exploit this observation, but this 2-dimension is an obstacle toward deciding whether something is solvable or not. And I have a conjecture that can kind of, we have a bunch of partial results, and I have a conjecture that unifies all this. Basically that if you can do a 2-set agreement, then everything is decidable. and not otherwise. But that's remains to be proved. So the last thing I want to talk about is some open areas. You know, if you're looking for something interesting to do in this area, so these are kind of big questions. I'm not going to tell you what to do to, you know, improve some recent paper to get, you know, paper accepted at the next PodC or something like that, because, you know, you can figure that out. You know, Hagit will tell you that. Yeah, I'm going to talk about big, sweeping, impossible problems that, you know. So one question is randomization. So all of the protocols that we looked at so far are deterministic. You know, they're either a solution or there's not a solution. There's a big literature on randomized protocols, even in distributed computing, where you know, consensus is impossible with read-write memory, but randomized consensus is possible. And there are a lot of interesting lower bounds and algorithms. What about randomized set agreement? You know, actually nobody knows the answer to that, really. What about, you know, randomized renaming, all of these things? It seems like this kind of topological approach might be useful for randomization. It's not too hard to formulate the problem in this language, but it's not obvious how to do it in such a way you can get answers. So I think there's a lot of interesting questions, you know, taking the machinery that we've developed in this course and applying it to randomized algorithms. And this is kind of a wide open field. Another issue is complexity. So all we've done is we say, yes, there is an algorithm, or no, there isn't an algorithm. If you try to look at the actual complexity, then all of the algorithmic constructions that we have are either constructions that we pulled out of the air, that is, you know, out of some conference proceeding, someone else's conference proceedings, or we have this construction where we say, well, there is a simplicial approximation. How do we do this? Well, it has to do with Lebesgue numbers, epsilons and deltas, and so on. And it always boils down to something saying, well, there exists a quantity that has this property. And in the mathematical tradition, we don't worry too much about what that quantity is. But in computer science tradition, for example, the size of the Lebesgue number determines how long your protocol runs, because it tells you how many subdivisions you do. And there's been very little progress on understanding the complexity of any of these algorithms. And that's something that I think is also would be extremely interesting to try to refine some of these arguments to talk about complexity as well as just existence. We've looked at tasks where everybody wakes up with an input, they compute for a finite amount of time, they choose an output, and then they stop. But it's also interesting to think about long-lived computations. That is, a computation that goes on forever. A server, you know, gets answers. Something like, you know, your internet protocols. You know, you're always reconfiguring the best path to from one place to another. And you get information that link is down, so you reconfigure it. You get information link is back up, and then you reconfigure it. And so having a system that runs forever and that reacts to outside inputs continually is something that that nobody's really applied this formalism to. So a naive approach, you'd say, well, if a finite computation is a finite simplicial complex, then an infinite computation should be an infinite simplicial complex. But infinite simplicial complexes are very tricky sorts of things to deal with because they're not compact and there are all kinds of mathematical problems with that. And so I think it would be very interesting to think about how to take this kind of formalism and talk about long-lived computations. You know, you could imagine it as, you know, the limit of a, you know, a sequence of finite computations, things of that nature. But, you know, these are all things that I think would be, even partial results here would be very interesting. You may have noticed that for colorless tasks, we had you know, all kinds of theorems up and down giving you necessary and sufficient conditions in very simple terms. But for colored tasks where your identity matters, we don't have nearly the same complete collection of results. For example, even for something like a renaming, we have this lower bound that works in some areas. We have this mysterious algorithm that works for the other one. We don't have any lower bounds for that case. We don't know whether this algorithm is optimal or whether there are even better algorithms, or maybe even better algorithms for numbers that have even more complicated properties. Nobody has any idea what's going on there. So once you have colored tasks, then you have this asymmetry where you have to be careful about what your input is. You have to make sure your maps are color preserving and so on. And so these are areas where much less is known. So we have partial results, but it's not entirely satisfactory because we just have, we're still short of having all of the results that we need to have a really satisfying theory in this area. Byzantine models and related things like omission failures and so on. We have a very simple fail-stop model where a process just runs along and it crashes. Meaning, if it misfunctions, then it just stops. You can imagine something where a process starts, dropping messages and not sending them, or something where it goes completely crazy and sends out, Byzantine messages. In principle, there's no reason this shouldn't apply, but nobody's ever done that. So I think, so that's also interesting kind of question. So these are deliberately phrased in kind of, very broad terms. I'm trying not to be as specific here, just to be kind of more inspirational. But I think, and it's not really the case, these are open questions not because generations of computer scientists have, been frustrated. I think a lot of cases, people haven't really looked at them. So that some of the results that we covered in this course have been around for 10 years, but they looked a lot different. When we first did these things, they had homology theory and all kinds of heavy-duty stuff. And we spent a long time basically trying to simplify the structure to kind of really understand what's going on. And I think what's going on here is a similar kind of thing where we haven't really started to work hard on these problems. And I think if you're looking for something to do, then these are kind of interesting areas where if you get results, I guarantee that people would be interested. Okay, thank you. That's it.